Hello, welcome back. Today I want to talk about Kruskal's algorithm and minimum spanning tree. What is a spanning tree? It's a minimum subset of edges that's needed to connect all the vertices together in a connected graph. For example, in this set of vertices, this will be a spanning tree. This is also another spanning tree, and this one is not a spanning tree because we can delete this edge and then all the vertices are still connected. So what is the minimum number of edges we need to connect n vertices in a connected graph? If we have one vertex, we need 0 edge. If we have 2 vertices, we need 1 edge to connect the 2 vertices. If we have 4 vertices, we need 3 edges. So we need a minimum of n-1 edges to connect n vertices. When we talk about spanning trees, we are often working with a connected and edge-weighted graph. Let's take a look at this example. This will be one spanning tree. If we add the weight of all the edges together, this will have a combined weight of 6. Here is another spanning tree of the same graph, and this has a combined edge weight of 5. And here will be another spanning tree, and this has a combined edge weight of 4. A minimum spanning tree is a spanning tree that has a minimum combined edge weight. So this one would be the minimum spanning tree of this graph. If the combined weight is maximum, then we have a maximum spanning tree. The minimum spanning tree or the maximum spanning tree, they don't have to be unique. One can have multiple distinct minimum spanning trees for a particular graph. To summarize so far, definition of minimum spanning tree is a set of edges to connect all vertices in an undirected graph such that the combined weight of all edges is minimum. Now let's use Kruskal's algorithm to generate a spanning tree of this graph. First, we sort all the edges based on the weight of the edge. In this graph, we see that there are 4 edges with weight 1. So we can pick any of these. So let's pick A and B. And we'll put this on the tree. Next, we pick another edge which has a weight of 1. So let's pick C and D. Once we put that on a tree, there is still no cycles exist. So we are good. Next, we put another edge on the tree. So A and C also has a weight of 1. And again, we check and there are no cycles. And then we continue. We add another edge, D and E, which has also a weight of 1. And also there is no cycles after we add this edge to the tree. So with 5 vertices and 4 edges, we have constructed the minimum spanning tree using Kruskal's algorithm. Now, a couple words on the implementation. We will use a heap to store and sort all the edges with weight, and we will use the union find structure to check for cycles. If you are new to union find, I include a link to my video on union find in the description below. Please go and take a look at that video. Now, let's use Kruskal's algorithm in a real problem. This problem is from HackerRank. I left the link to this problem in the description below. We are given an undirected graph. Our job is to return the combined weight of all the edges in a minimum spanning tree of this graph. The minimum spanning tree for this graph is on the right, and it has the combined weight of 12. The implementation I will use is in C#. This code is provided in the GitHub links below. Implementation uses union find. If you're not familiar with union find, I would suggest you watch my video on union find, and I provided this in the description below. We start off with some of the boilerplate codes for union find. We would have the find parents function and also the union function. And also we would have the parents array. And I will start off initiating the parents array where the parents of each node is the parents of itself. Now let's go through a very simple graph. Here we have a graph with 3 vertices and 3 edges. We will extract the information of the graph and put this in a heap. So the 2 poles we store on a heap are 1, 2, 2, which represents there's an edge between 1 and 2 and has a weight of 2. So it will be 1, 2, 2, 2, 3, 2, and 1, 3, 3. These are sorted by weight. So the lowest one is 1, 2, 2, followed by 2, 3, 2, followed by 1, 3, 3. And I also initiated the variable weight that will be the accumulation of weights of the MST, and that is the value that we will return at the end. Now that we have all the edges on the heap, we can just dequeue each one and construct the MST. So the first item we dequeue is 1, 2, 2. So we make the 1, 2 edge here, and we update the value of the weight for 2 for this edge. Every time we dequeue an edge from the heap, we always check whether the cycle exists. So that's what this line is for, to see if the parent of that node is the same parent of the other node. And if it's not the case, then we know that there is no cycle, and we'll perform a union operation. Then we will update the weight value with the edge weight. When we perform a union operation, basically we are saying that these nodes are now together in the same disjoint set. This is the operation I was referring to when I say I add the nodes to the minimum spanning tree. Going through this example, the next item is 2, 3, 2. We will dequeue from the heap, and then we will add this to the minimum spanning tree. And the weight of this edge is 2, so we update the value of weight to be 4. And we check there are still no cycles, so we are good. The next item is 1, 3, 3, and we check 1, 3 are already connected, so we will skip this one. Now we have completed the minimum spanning tree of this graph, and then we will return the weight of 4. Now a couple words on the time complexity. To initiate the parent array, that is O of n. To heapify all the edges, that is O of e, where e is the number of edges on the graph. In the while loop, we go through all the edges, and then we will check whether there are cycles between the two nodes for each edge. And if there's none, then we'll perform a union function. And we have the find parent operation, and we have the union operation for each edge. That's e times log n. For dequeuing of each edge in the while loop, that is O of e log e. So O of e log e is the dominant term. So the complexity of everything here is O of e log e. Now there is also an optimization one can introduce, because for MST we only need n-1 edges, so we can also track how many edges we have already included in the MST. For MST, we can either use Kruskal's algorithm discussed here, or we can use Prim's algorithm. Personally, I find that using Prim's algorithm is probably faster. It really depends on how you implement union find. And I feel that for interview purposes, writing all the codes for union find might take a little bit more time. But all these you can discuss with your interviewer. Okay, let's take a look if this works. And it looks good. Next time, we will use Kruskal's algorithm to solve another similar problem. Hope to see you then.